this CubeSat revolution really has changed the world in a positive way. That being said, those space guys just need to stop complaining. When they put something into space, they act like it's this, engineering marvel. They've got one atmosphere of pressure to deal with between the inside of a platform and the outside of the platform. Try putting something on the bottom of the ocean where you have hundreds of atmospheres of pressure. Everything needs to be perfect to, millimeters, otherwise it'll literally explode or implode. We're putting our sensors in acidic baths of some of the most corrosive stuff known to man, being salt water.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel and this is a podcast for the geospatial community. My guest today on the show is Chris Verlinden. Chris is the CTO and Vice President of a company called Applied Ocean Sciences, and today on the podcast we're talking about using acoustics to map the marine environment and mapping the acoustics in the marine environment. So this is a pretty dense conversation and you understand what I mean when you get into it. But here are a few key points I want you to listen out for. So the difference between soundsheds and soundscapes, the ocean of things, using whales as CubeSats, the fact that we know more about the surface of Mars than we do about the seafloor of our own planet, and how space is hard but the ocean is harder. Oh, and there's a big shout out to all the bubble curtain people out there towards the end of the conversation. So as you might be able to tell from those key points there, we cover a lot of ground in this conversation. And I think this episode ties in really nicely with a previous episode called Mapping the Ocean Floor. So this was published in January 21, and I'll put a link to that in the show notes, but you can also find it if you just scroll back through the archive on your podcast player. Just before we get started today, I want to say a big thank you to our sponsor Regrid. So Regrid are the parcel data people for the US. So think of parcel data as being the legal boundaries of properties. And America is made up of these legal boundaries, and they have owners, they have assessments, they have current land use. And these boundaries surround everything: homes, parks, commercial buildings, farms, wild places, everything. But wait, there's more. It's not just parcel data. You can also get parcel data with matched secondary addresses. So what this means is that each parcel, it comes pre-joined with all known addresses in the United States. But wait, there's even more. You can get parcel data with matched building footprints. And what this means is that you get a geometry of the building footprint that lands in the right place in the parcel data, and these two things are matched. So growing up in New Zealand, every time somebody in the media said, wait, there's even more, it usually meant that there was a free set of steak knives involved with it. Unfortunately, this is not the case with Regrid. It's just parcel data with matched addresses and matched building footprints. But if you're also interested in steak knives, maybe you should talk to them. Maybe Regrid can help you with that too. Hey Chris, welcome to the podcast. So today we're going to be talking about mapping the acoustic marine environment and using acoustics to map the marine environment. So I'm really looking forward to this conversation. I wonder if, for the sake of context, if you could take the time to just introduce yourself to the audience, please.
Sure. Well, thank you very much for having me. Happy to be here. My name's Chris Verlinden. I'm an oceanographer and acoustician. I'm originally from Portland, Oregon in the United States. Spent about 14 years in the Coast Guard as an officer, primarily serving on icebreakers in the Arctic. I spent the last few years of my career on loan to the Navy doing ocean acoustics research, everything from finding submarines to finding whales. And I got out of the military about 4 or 5 years ago and helped found a small company called Applied Ocean Sciences, where I currently serve as the CTO, and we do research in ocean acoustics and marine environmental protection.
So I noticed during the introduction there, you refer to it as ocean acoustics. A lot of the time I hear people calling acoustic environments soundscapes, but for me it would make much more sense to call them a sound shed in the same way we talk about a watershed or a view shed. For me, I imagine that this acoustic environment has geographic limits. Could you explain to me why we don't often refer to this as being a sound shed?
Sure. I actually love that question because I'm secretly starting the movement to start the term sound shed because I think it does have some applications. First of all, I refer to the study of ocean acoustics, which is really just the study of sound in seawater, how sound propagates, the impact it has on the environment, and how you can use sound to sense the environment. When I use the word soundscape, I think of it as a way to describe everything that you'd hear in the ocean. So it's sort of the cacophony of man-made sounds from ships in industry, oil exploration, the sound of biologics like marine mammals, fish snapping, shrimp, croaking fish, things like that, and natural sounds, everything from breaking ice, breaking waves, wind, and seismic activity like earthquakes and volcanoes. And so I think of soundscape the same way I think of like a landscape. If a landscape, if you're standing in a beautiful environment, is everything that you can see. Well, the soundscape's everything that you can hear. Whereas, I think of the term like viewshed or watershed. A watershed is, an area, delimited by, all the water in this area flows, to a single point. Or, a viewshed is from this single point. These are all the places that I can see. And so I think a really appropriate of the terms soundshed might be used to refer to, the sound footprint of a single source, or maybe the sound footprint of a single receiver. And so what I mean by that is, if I have a microphone or an underwater microphone called a hydrophone in this location, what are all of the things I can hear? And if I look at the footprint of everything I could hear, to me that would be the sound shed of that microphone. And similarly, if there was a whale, let's say a blue whale, calling at its usual noise level and frequency, there would be, based on the ocean conditions, a certain area over which you could hear that whale. So to me, the sound shed would be the area over which you can hear that single whale, whereas the soundscape would be the abundance of sound in the ocean. It's the accumulation of all of the various sounds that you're hearing. And a soundscape might not have clear definitions because depending on the time, or what's happening, or what the dominant source of noise is, the variability of the soundscape will change. For example, if a hurricane's moving through the ocean, in ever you're within a few hundred miles of this hurricane, all you're going to be able to hear is breaking waves and wind and the noise from the hurricane. Whereas similarly, if you're in an area near a shipping port, all you're going to be able to hear is these ships. But that could change. Maybe the port closes at night, and over the course of the day, that soundscape changes. And so to me, soundscape describes all of the sounds that you can hear in a given area, and those geographic boundaries will change and shift over time. So I like the term soundscape to describe that.
So when you were describing soundscapes, you're talking about all of the different noises you could hear. You gave us a bunch of different examples, and you also mentioned this idea of using sound to sense the environment. So oftentimes we think about remote sensing from satellites, for example, we'll think about active and passive sensors. When we think about active sensors and sensing the marine environment, people listening to this podcast will be familiar with using acoustic measurements to measure bathymetry, for example. I wonder if you could give us a few examples of passive sources of acoustics that we can use to measure things and what we can measure with them.
Well, I love that question because this is a question I've devoted my life to. So I'll get really excited. I don't know if any of the listeners will get as excited as me, but I think it's a pretty interesting topic. So first of all, just like with remote sensing from space, where you have active sensors like synthetic aperture radar and passive sensors like just collecting imagery, you have that same paradigm in the ocean. Fundamentally, when you're studying the ocean, you have to use sound because sound is how we see underwater. And what I mean by that is, all the electromagnetic radiation, all the visual band optics, the light just doesn't propagate very well underwater, and neither do most frequencies of radio that we can use for communication. So what that means is if we want to image the bottom of the ocean, whereas on land, we know we could use radar, we could use LIDAR, all the DARs don't work underwater. We pretty much have to use sound to image the environment. Similarly, marine mammals use sound to navigate, find mates, communicate. So if you want to communicate, if you want to see, if you want to sense your environment, if you want to navigate, sound really is your only option. And just like in space and just like in air, where you have passive and active means to do all of those things, similarly, you have active and passive acoustics. So, active acoustics would be where you transmit a sound, and use the way that that sound interacts with the environment to learn something about your environment. Just like you pointed out, the real quintessential example of that is bottom mapping sonars, or multi-beam sonars, bottom penetrating sonars, where you put out a pulse of sound, you wait for the reflection off of the bottom of the ocean, and sub bottom layers, even within the bottom, you can image what's underneath the seafloor, and you use the travel time of that reflection to get back to your sensor in order to determine the distance to all of those things. And if you're determining the distance to all things in all directions, you start to construct an image of your environment. That's all well and good. Active acoustics are a very effective way to measure certain things in the environment, but there are downsides. One of the downsides is some of these active acoustic techniques can be damaging to the environment. It can be harmful to marine mammals and fish that use sound to navigate. Also, if in this new paradigm of swarms of autonomous vehicles exploring the ocean, every watt of power matters. And if you have to put out active pulses of sound, you're going to kill your battery a lot quicker. So passive sensing techniques also have the advantage of being far less energetically expensive, and also the equipment is far less expensive. So I've really devoted my life to the study of passive acoustic sensing technologies. The easiest example is passive sonar compared to active sonar. If I'm looking for a submarine with active sonar, I put out a ping. I wait for that ping to reflect off of objects such as submarines in the water. If I wanted to find that submarine passively, I just have to listen very, very carefully for the sound that that object, that submarine makes, and then use triangulation. So use the direction that that sound is coming from on my array of hydrophones to determine the location of the source. But I think you really hit on a really interesting point, which is that passive acoustic sensing isn't limited to just hearing whale song or finding submarines. You can do a lot of really, really cool things passively. There was a really wonderful paper written in the 90s by a scientist at Scripps, Mike Buckingham. He was actually on my committee, and he's a brilliant and wonderful guy. He wrote a paper called Acoustic Daylight. And what he did was he drew a comparison to the way that we use our eyes to see and sense our environment in air to what we might be able to do with acoustics underwater. So think about the way that we interact with and that we sense our environment around us, above water. We use our eyes. Our eyes aren't active sensors. We don't have laser beams shooting out of our eyes, like LiDAR measuring reflections off of everything. We just take the ambient electromagnetic radiation or light that's reflecting off of objects and scattering all around us. We receive that light on some darn good arrays, being our eyeballs, and do some very clever signal processing in our brain. And we're able to reconstruct an image of what the world around us looks like from nothing but backscattered and ambient light. So Michael Buckingham wrote this paper of how we might be able to use acoustics to do the same thing. And he used noise from things like breaking waves on a pier or snapping shrimp in order to image objects underwater. It's a non-trivial problem. It is very, very challenging to do. But fundamentally, he opened the door for a lot of really, really interesting work in using passive acoustics to sense the environment, using the noise that's already in the environment to measure the ocean. And so a couple cool examples of that are we've used noise from ships to measure the temperature and salinity and possibly even the pH of the ocean using the way that the temperature, salinity, and pH of the ocean affects how sound propagates through seawater. And so without putting any extra sound into the water, we can sense the environment. And that can help with all kinds of things from climate and weather forecasting to military operations to understanding ecosystem dynamics. And a really, really interesting example is another dear friend and colleague of mine, Dr. Aaron Thode. He wrote a paper a while back where he used blue whale calls to invert for or to measure bottom properties of the ocean, and more recently, even seawater properties using calls from whales. And I think that type of work is very, very exciting.
So you mentioned this idea of, using an array of sensors to gather this information. You talked about it being a non-trivial problem. When you were talking about using the acoustics from a ship to measure seawater temperature, I think you said, what kind of sensor array are we talking about that we need to have in place in order for that to make sense?
Well, I'll let you know when I figure that out. Like I said, it's a non-trivial problem, and there's a lot of really, really bright people working on it. In fact, I have a current ongoing research program with the Office of Naval Research studying exactly that problem, which is what sensors and what combination, what configuration do we need in order to make use of those types of sources to measure the ocean? What I want to do is I want to create algorithms that can take an arbitrary system of hydrophones or sensors anywhere in the ocean and quantify how well I can use those sensors to measure the ocean. Because that's really the key, right? You're not going to pursue a new remote sensing technique unless you really understand how well it's going to perform. And because some of the mathematics that go into inverting for ocean profiles and sound and seawater properties using noise from ships really are non-trivial because you don't know exactly where that ship is. You need to localize the ship. You need to account for any type of timing or position offsets in both your sensors and the receiver. And you need to measure the properties of the ocean all in one big mathematical calculation. And there's a whole field of mathematics that really center on how you can cheat in that problem, how you can use prior information, things like AIS ship tracking data, and the fact that your array is only so long. So your hydrophones can only vary in certain positions. And so I've really made a career out of finding clever ways to cheat in order to do better with less information on measuring the ocean with sound. And I'm currently working on trying to find ways in order to determine the information content of sound on arrays of hydrophones, just like that, so that we can use that to answer your exact question, which is, what do I need to measure the environment? And the answer is always as many hydrophones as possible, as perfectly surveyed as possible, with as good of synchronization as possible. But how good is good enough, and how many phones do you really need? I think that's really an open question, and that's something that we're hoping to answer.
I totally understand this is a non-trivial problem, and this suggestion here is not like an attempt to say, hey, what, just do this. I heard you mention AIS data. So AIS data is this broadcast that comes off ships, and it gives you speed, direction, and a little bit more information about the actual ship, and also the position of the ship. Can we use that and say, oh, we know that ships travel along these lanes here, and put an array of hydrophones along those shipping lanes, and start doing something there, because we know where the ship was, we know the size of the ship, we can make some assumptions about how much noise it was producing, and with an array of hydrophones that hopefully weren't moving, is that like a feasible way forward when we think about using these passive sources to map the marine environment?
Hey, man, you got to keep quiet about that. You're going to give everyone all my ideas. Yeah, absolutely. That's something that I've been wanting to do for ages, and we've got colleagues at University of Hawaii who've been thinking about that same thing for a long time as well, instrumenting underwater cables and things that are already on the bottom of the ocean in areas where you have access to sources of sound like ships, in order to do exactly that. And like you said, the advantage of fixed sensors is you only need to survey their location once and they don't move. I mean, there's a lot of advantages to those types of fixed sensors. So yes, I think 100%. The more hydrophones that are out there in the ocean, particularly, you shouldn't put them out randomly. There will be places where we have more data, like you said, if there's a place next to a shipping lane or something like that. But then you also have to think about places where we really need those measurements. So there's a lot of places where we just kind of know what the ocean looks like, either because we have, a lot of sensors already in place, or because the variability of the ocean in those areas, isn't so significant. A good example of that, I've done a lot of acoustic experiments off the Pacific Northwest. I could probably draw for you what the temperature and salinity profiles looked like 500 miles off of, the Olympic Peninsula in Washington State right now, and be within a degree or two. Because the fact is, the variability is very predictable and very well understood there. So with a couple of sea surface temperature measurements, a few floats, a good oceanographer can tell you really what's going on with the dynamics in that area fairly accurately. If you look at a place like the North Atlantic Ocean, off of the UK, for example, holy cow, that is a complicated ocean. If you take a measurement in one place and you take a measurement 10 kilometers away, I don't know what they're going to look like, but I guarantee they're going to look different. Similarly, a few hours. There's a lot of really complicated oceanographic processes, deep convection sites where water sinks and forms the ocean bottom water and deep water masses that spread throughout the ocean, eddies, currents that meander hundreds of kilometers, on a timescale of a few days. And so oceans like that are very, very important to get more measurements from. And I think the real holy grail of ocean measurements right now is the Arctic. The Arctic is for much of the year covered with ice. And that makes it very, very difficult to get research vessels and most of the types of sensing platforms that we have access to underneath the ice. The ice blocks our, satellite remote sensors, so sea surface temperature measurements and things are very, very challenging to get. And it's one of the most critically important places to measure because it's one of the places that's changing the fastest due to climate change. And so acoustic measurements for measuring the ocean properties under the Arctic are incredibly important and similarly very challenging because not a lot of ships in the Arctic. And like I said, if you need to know as much as you can about the sensors in the environment in order to use those sensors to make meaningful measurements of the environment, well, the Arctic, where there are a lot of unknowns, is a challenging place to work. And I think that's why, your question was a really good one. You said if we just put these fixed sensors where we know exactly where they are all over the ocean, and we just use all the sound sources that are already in the ocean to map and measure ocean properties. And I think the answer is yes, but there will be places where that's not practical. And that's why I think we need to do a lot more work at using moving platforms and sensors that might not be perfect. There was an interesting study done by DARPA here in the United States recently called Ocean of Things, where they wanted to put tens of thousands of biodegradable floats out in the ocean and instrument them with sensors, including potentially hydrophones, where these things are just sort of drifting around and moving all over the place. And that creates challenges because you need to really get the position of those sensors very accurately. You need to get timing synchronized perfectly. But if you can do that, you could potentially use all of those sensors kind of like, the CubeSats, but in the ocean. And so there's a lot of really exciting work going on in this area. There's a company I love to work with called Subsea Sail that's making this autonomous sailing vessel that's a fraction of the cost of anything else that's out there, that you could put hundreds, if not thousands of them out all over the ocean and position them optimally in order to get the best possible measurements of the ocean everywhere. And it's a silent sensor because, it's a sailing vessel, and semi-submersible nature makes it a really quiet platform. So that's really, really exciting work. You could also instrument platforms that are already out there, things like putting tags on whales, and then all of the tags that are on animals that are moving around, already sampling the environment. You can collect that data and use that to make more meaningful measurements of the ocean as well too. And I think while we're talking about this, to me, an oceanographer, it's sort of self-evident why we need to understand these properties of the ocean better and why we need to map these properties of the ocean better using sound. But it might not be, so obvious to everyone. I used to teach oceanography at the Coast Guard Academy, and I'd always start off with a description of why it's so darn important to get these measurements. And I always use El Nino as the example. El Nino pisses me off, and it should piss off everyone. El Nino is a phenomena where warm water from the Western Pacific sloshes across the ocean into the Eastern Pacific, creates, a big pool of warm water, which causes air to rise, precipitation, disrupts global weather patterns. It can cause floods, famine, disruption to crop cycles, disruption in ecosystems all over the world. It can put thousands of people out of work. It can cause starvation, billions of dollars in economic disruption, thousands of lives impacted, people dying from the impact of El Nino. El Nino is billions of joules of energy. When you talk about that much water, it's dynamics that we understand. We get geophysical fluid dynamics, we get how water moves, and yet we cannot predict El Nino. This is a solvable problem in our time. If we understand the ocean better, if we make better measurements, if we make advances to ocean modeling techniques and ocean sensing techniques, including the acoustics ones we're discussing today, it's achievable to do things like predict El Nino. I mean, if we can do that, we can save lives, we can preserve the economy. Everybody wins. I mean, if El Nino doesn't keep you up at night, it should. These are solvable problems in our time if we can just make better measurements of the ocean. All we need to do is make better measurements of temperature, salinity, pH, and we can understand, the future of ecosystem, the viability of fisheries, future weather and climate patterns. And that's a really, really exciting thing. And these types of measurements are a critical part of that.
Well, Chris, I love talking to people like you. You know so much and you're so enthusiastic about the problems that you're trying to solve. I just want to wind back the clock a little bit because you said a couple of things that you need to go back and clarify for me. You talked about the ocean of things. It sounded like you were talking about using marine animals to sort of crowdsource this mapping work that needs to be done, maybe putting sensors on whales. Can you tell me more about that, please? Earlier in the conversation, you talked about using whales or using their acoustics to passively sense the environment. Are we then talking about putting a sensor on it and using a whale like a CubeSat, having it travel around the ocean? We know when the acoustic sound was emitted, and we can measure when it comes back. Am I on the right track here?
Yeah, you sure are, but don't tell anyone because people will think we're crazy. It does sound a little crazy, right? Using animals as sensors, but let's talk for a second about how maybe it isn't as crazy as it sounds. So, first of all, DARPA Ocean of Things, it was a program that they created in order to try to see if you could make tons of measurements of the ocean in order to resolve all of the things that we just talked about. If you could instrument the ocean to that degree, you could do things like predict El Nino. You could track where whales are in order to, more accurately predict and therefore mitigate the human impacts on these ecosystems. And so having more sensors in the ocean is critically important. And I think DARPA Ocean of Things really highlighted a couple of things. First of all, it showed the importance of it. And second of all, it showed the doability of it. And that's probably not the right word, but sensors, electronics, data exfiltration, these things have all gotten cheaper and more available over the years. It used to be that if you wanted a temperature sensor in the ocean, you better have 70 grand. And now, there's an open CTD project. You can Google open CTD on the internet. That's conductivity temperature depth sensor. And you can make it for a couple $100s worth of parts and a PVC pipe, and it'll work pretty darn good because, there are these commercial off the shelf, electronics. There's hacker websites, there's Arduinos, Raspberry Pis, Odroids, Teensies. There's access to technology that we never had before. Similarly, there's, Iridium satellite constellations, so you can get data off of any of these instruments. Starlink, and Kepler Space, a really exciting company out of Canada that's making a really nice communication constellation. The ability to interact with sensors, low powered, low cost sensors all over the world has never existed before, and it does now. And that's a really, really exciting time. I think in oceanography, we're entering into sort of a new paradigm. It's kind of a revolution right now. I mean, it's something similar. The space industry, I would say, is about 10 or 20 years ahead of us. In space, it used to be that there were a few dozen satellites. They cost billions of dollars. They were the size of school buses, and they had really nice cameras or really nice sensors, but you only had a few of them. Now we have tens of thousands of sensors and communications hubs, and each of those cameras might not be as good, but when you combine the information from tens of thousands of, essentially what are lower end, lower cost, lower size platforms, you get a lot more information, and we've never known more about the world. We just got that memo in oceanography, and we just realized that having more sensors is good, and having more sensors needn't be expensive. I mean, so like I said, companies like Subsea Sail making that inexpensive surface platform, programs like DARPA Ocean of Things, another really exciting company so far. They have series of floats, and they're using that information to optimize shipping patterns all over the world using all those extra environmental measurements. I think it's established that having lots of sensors, even if they're poorer quality sensors, even if they don't report as often, or even if you don't, let's say in the case of whales, have complete control over where they go, that's a really good thing. So now let's talk a little bit about, what would happen if you instrumented a whale or an elephant seal with a sensor. I say elephant seals because they're one of the deepest diving marine mammals. They have a higher blood oxygen content, a higher concentration of hemoglobin in their blood than any other animal I'm aware of. They can stay down forever. Don't quote me on this, but order hours, and they can dive super deep. So you put a temperature, sensor, a CTD, like we just talked about, on an elephant seal, you'll get really incredible profiles of the ocean. And a lot of researchers have done some really exciting work doing exactly that. And so the idea of putting sensors on animals isn't that crazy. Now let's put a hydrophone on those animals. Well, first of all, you can listen to what the animal's doing. That's really, really important to understand the way that animals interact with their environment, how whales use acoustics. So just the biological information we could gain from that would be incredibly valuable. But also, it's not so crazy to then start thinking about, well, if we can synchronize those clocks, if we can localize those animals using the acoustics around us and other technologies, perhaps we can coherently process these hydrophones across groups of animals, just like an array of hydrophones, just like what we use for finding submarines and whales when we have complete control over them, and use those moving arrays of hydrophones to make measurements of the environment. So I think there's two really critical things to understand here, and that's that you can use ambient noise to measure the environment. And I think that's something that a lot of people don't fully understand because we think of using sonar, and I talked about maybe you could use the noise of ships, kind of like a sonar to you know localize things underwater or to measure temperature, salinity, things like that. But you can also use the differences in ambient noise from things like ships and things like waves and stuff like that, recorded on groups of hydrophones. You can use the difference in order to measure, how much time it took for the sound to travel between those two instruments. And because temperature and salinity affect the speed of sound, that can give you estimates of the temperature and salinity of the ocean. And moreover, you can use passive acoustics and sources of opportunity like whales and ships to measure the bottom, both the location, the shape of the bottom, as well as what the bottom is made out of. And a good example of that is a paper again by Martin Siderius at Portland State, who created something called the passive fathometer, where essentially he takes an array of hydrophones, no sources of sound anywhere, and he does something called beamforming, which is a signal processing technique that allows you to listen in just one direction. He beamforms up and he beamforms down. And he says all the energy coming from the seafloor is coming from the surface, just reflected off the seafloor, because all the things that make sound are at the surface. And so he says the time difference between the up beam and the down beam has to be the travel time between the hydrophone array in the bottom and back up. So just like an active sonar, he's able to use the ambient noise of breaking waves and things at the surface in order to image the bottom, a passive fathometer. It's not inconceivable to think you could do passive multi beams, passive sub bottom profilers. And Martin and I have actually written papers about, measuring bottom loss, which can tell you what the bottom's made out of. So yeah, I don't think what you're saying is that crazy. Where if you have passive hydrophones anywhere and everywhere you can get them, whether or not they're on floats, if they're on animals, if they're on fixed platforms all over the ocean, I think you can make very, very meaningful measurements of both the soundscape, which is important in its own right, as well as the environment, to include temperature, salinity, pH, and bottom properties, which matter for ecosystem dynamics, economics, oil and gas exploration, a national defense. If you're talking about finding submarines, this stuff matters. And I do think having hydrophones everywhere, including potentially on biological CubeSats, would be really beneficial.
So this is a real eye opener for me. This idea of using biological CubeSats, as you call them. I think you were referring to the idea of using groups of these in kind of a mesh network to image our environment, to sense our environment. And then I think when you started making those comparisons to new space, to what's happening in the space industry at the moment, it really opened my mind. And so I guess my next question is, why do you think we are pouring money into space platforms, to Earth observation platforms in space as opposed to Earth observation platforms in the water? Is it more difficult to put things in the water than in space, do you think?
Well, you really struck a sensitive spot for me there. So I apologize if I offend any of my space colleagues now, but yeah, I think that's exactly why. Don't get me wrong; the assets we're putting in space are very valuable. The measurements we can make of meteorology and things that really matter for people are important. The communication constellations, this CubeSat revolution really has changed the world in a positive way. That being said, those space guys just need to stop complaining. When they put something into space, they act like it's this, engineering marvel. They've got one atmosphere of pressure to deal with between the inside of a platform and the outside of the platform. Try putting something on the bottom of the ocean where you have hundreds of atmospheres of pressure. Everything needs to be perfect to, millimeters, otherwise it'll literally explode or implode. We're putting our sensors in acidic baths of some of the most corrosive stuff known to man, being salt water. Working in the ocean is so darn hard and it's expensive. And I think that's part of the reason. Yes, space is sexy, space is important, and space-based sensors can make really meaningful measurements in our lives, and space-based communication assets can really, improve our lives. But understanding the ocean is critically important as well. It is very challenging and it's very expensive. Which is why you hear people say things like, we know more about the surface of Mars than we do the floor of the ocean on our own planet. And I once wanted to examine how true that statement was. And I was hosting a panel. I was really blessed, honored, and lucky to be able to do this for the American Geography Society, between Don Walsh, Bob Ballard, Sylvia Earle, and Catherine Sullivan, for really just pillars in the ocean exploration community. And we had this exact discussion. I asked them, to what degree is it true that we know more about the surface of Mars than we know about the seafloor on our own planet? And it really depends on what you mean. We have a bathymetry map of the whole world. There aren't places where we know nothing, because between, again, I have to tip my hat off to the space people, satellite derived gravity measurements, gravitational anomalies, shuttle radar topography mission, things like that. We've been able to map out with at least very poor resolution everywhere on the surface of the Earth. But if you want to talk about resolution that's good enough for things like, seismic exploration, understanding where mineral deposits are, understanding what the bottom's made out of well enough to know what might be able to live there, important ecosystem parameters, well enough to be able to model the acoustics in order to do things like find submarines or whales better. Then you're talking about, the need for maps of the seafloor with, resolution, better than 10 meters. And we don't have that. Depending on who you ask, I think it's between 5 and 15% of the ocean is mapped well enough to do that, whereas the entire surface of Mars is. So, by at least some very meaningful metrics, we do know more about the surface of Mars than we do about, the seafloor on our own planet. And I think that's problematic. There's a lot of really exciting efforts going on. I think Seabed 2030 is one where there's a lot of academic institutions, government programs, research labs, nonprofits, companies. They've combined together to try to create a sort of comprehensive seafloor map of the entire world by 2030. And that's a really exciting effort because, well, we need that. And it also represents this level of international cooperation, which I think is rare and incredibly powerful. And it shows you that it can work. And so I think we should use that as an example of ways that we can share data more effectively on a lot of different levels. Acoustic data, temperature, salinity measurements, things like that. Catherine Sullivan, the former director of NOAA, the first person to have walked in space and gone to the bottom of the Marianas Trench, a low key hero of mine. She once said we need to API the ocean, and really what she meant is we need to work on data availability, data sharing, just like those folks who are working on the seafloor map for 2030, and we need to do that for all of our ocean measurements. So your question had to do with drawing comparisons between space and ocean exploration, and I don't want to take away from how challenging, how exciting, and how impactful space exploration and sensing is, but ocean exploration is incredibly important as well, and less resourced, and I would say less reported on if you look in the news. But I do think that's changing. I think that people are seeing that sensors are becoming more affordable. The problems that we can solve by understanding the oceans better are coming into our daily lives more. Things like understanding if storms are going to get worse or better, with climate change. Things like knowing which fisheries are healthy. Things like knowing which coral reefs are going to die and which sites might be viable for coral reefs in the future. People are starting to really understand how these things map to their daily lives, and I think as a result, we're going to see a real increase in how much people care about and think about the ocean exploration and ocean sensing in the future.
I just want to try and make one more point here about this before we move on and perhaps talk about noise pollution and what that means for the ocean, how we map that. But when I was listening to you talk, then you talked about being good enough. Like you talked about the bathymetry model that we have for the deep oceans, and you were saying it's not good enough to accurately model the acoustic environment, for example. And early on in the conversation, we are talking about acoustics is the way we see underwater. So is this actually a limiting factor when we think about that bathymetry model that we have today, is that the limiting factor when we think about seeing underwater, about sensing our marine environment?
Yeah, yeah, you're darn right it is. Think about it this way. All over the world, people are talking about 5G communications now. 5G communications could be very wonderful, very high bandwidth comms everywhere, but it's a challenging communication media to work with because 5G doesn't travel through objects. Heaven forbid there are leaves, in the way. And so having really incredibly accurate maps of the landscape is really, really important for understanding this, 5G communication infrastructure. So there's been a really sharp increase in the commercial, as well as government need for very, very accurate maps of the surface of the planet. And that same thing is true, although maybe less popularized because there are less people needing Wi-Fi and needing to Google where the nearest Starbucks is on the bottom of the Marianas Trench. But the problem's the same as important. In order to understand what you can communicate with, what you can see with acoustics underwater, you need to be able to understand what the bathymetry looks like. And similarly, unlike, well, it's true in air to a degree as well, where radio propagation depends on atmospheric properties. You can get ducting things, and for certain things like long range radio communications over the horizon radar, you need to understand those things intimately. But for knowing whether or not you're going to get Wi-Fi, you don't necessarily need to pull out your temperature sensor and measure the humidity, but you do need to do that underwater. If you want to know, let's say you want to know where you can hear a humpback whale. You put out a hydrophone, let's say, near a shipping lane, because you want to be able to warn mariners if there are a lot of whales in the area so they can slow down. Nobody wants to hit a whale. If you want to know where your hydrophone can hear whales, you need to know the bathymetry perfectly. I mean, as well as you possibly can, within a few meters. You need to know, that the depth accuracy everywhere. You need to know what the bottom is made out of. You need to know if it's sand, is it rock? Is there sand with a little bit of rock underneath it? You need to know the temperature and salinity of the ocean everywhere because temperature and salinity affect the speed of sound, and the speed of sound can cause it to refract, differently and bend back up to the surface or possibly down into the bottom. And finally, you even need to know the pH because the attenuation of sound is dependent on the pH. So if you really, really want to understand your shed, going back to what we talked about earlier today, you need to know as much as possible about the ocean. But there's hope because if you have hydrophones out in the ocean, you can learn more about the ocean that sort of improves your models. And so good enough, is just like, understanding the landscape well enough to do 5G communications. In order to do ocean sensing, we need to know the ocean as well as we possibly can. And here's an example of this. Whales, when they interact with their environment, they're doing it acoustically. They can't see very far underwater. So if a beluga whale wants to know where its food is, it's finding its food with acoustics. If it wants to know, it knows its food likes ocean environments of certain types. Maybe they hang out on ocean fronts, boundaries between warm and cold water. Maybe the food likes to live, above uh, ocean bottom made of certain properties. And so whales know what the seafloor is made out of. They know where ocean fronts are. They know how to navigate. They know how to find mates. They know how to find prey. They know how to find dangers in their environment. They know a lot about their environment that they're learning acoustically. And we've really, really only scratched the surface of what we can do with acoustics. Yeah, sure, we can find a submarine, a giant, giant hunk of steel underwater. Good for us. But we don't know where every single ocean front is everywhere all the time. We don't know what the bottom's made out of everywhere, and we spend a lot more money than beluga whales do. Beluga whales keep me up at night, and they should keep you up at night at too. I helped with a study by some researchers at Woods Hole, including a gentleman named Aaron Mooney, just a really brilliant scientist who was looking at how well beluga whales could direction find. And one of the things they found is that they can determine the direction sound is coming from something like an order of magnitude, 10 times more precisely than they should be able to, given the size of their sensing organ. The frequencies of sound they're looking at. They can defy modern mathematics in ways that we don't understand. If we can understand that a little bit better, then we can figure out how to use ocean acoustics to sense our environment a little bit better. And then, we'll be able to measure the ocean better so that we can understand, sound propagation well enough to predict how we can communicate and how we can detect submarines and where there might be underwater deposits of minerals, all that stuff. And also we can understand the environment better for its own purposes, for understanding ecosystem dynamics, marine and environmental protection. If you know where coral reefs are dying, you know where to focus. If the viability of the ocean for certain species, you know where to concentrate your efforts. So I think there's a lot of really, really exciting unturned rocks in ocean acoustics and mapping the ocean with sound. There's a lot that we don't know. And as a scientist, there's nothing more exciting than having a field where there is a lot that we don't know. There is just an abundance of discoveries to be made that have world changing applications. To me, that's why studying sound in the ocean is so exciting right now, is we clearly have a lot of really big problems. Think El Nino, think hurricanes, think finding submarines, and there's a lot that we don't know if we reflect back on the beluga whale and everything they can do with sound.
So up until now, we've been talking about using sound to map and measure the marine environment. I'd like to sort of move on now and talk about mapping and measuring the sound in the marine environment. So when we think about sound in the marine environment, a lot of us will think about pollution, noise pollution. And I guess my question is, how do we define noise pollution? Is it simply all anthropogenic noise that is put into that environment? Is it a certain frequency or over a certain time period? Could you give us a working definition of noise pollution when we think about the marine environment?
Well, sure. I'll give you a very jaded definition first. If you're in the European Union, you define noise pollution as ambient noise created by humans that can be harmful to the environment, defined as marine organisms or anything else. We don't define underwater sound as a pollutant in the United States as of yet. The Noise Pollution Act, I forget the exact name of the legislation here in the United States, really only defines noise pollution as it affects human beings. So noise pollution for us is defined at, if you have a large industrial facility next to a neighborhood, if it's creating sounds that are harmful to either creating stress in or physical damage to human beings, then that's a pollutant. But underwater sound, where there aren't a lot of human beings living, is not currently classified as a pollutant in the United States. And I think that's going to change very, very soon. And I think we've already seen the beginnings of it. There's been a lot of development lately in offshore wind, which I think is really, really wonderful here in the United States. It's existed for quite a while in much of Europe, but we're really starting to hit it hard in the United States, which I think is a really, really good thing. And these offshore wind developers, having come from Europe, where they've already had to, before they get a project approved, go through the process of determining what the environmental impact of these platforms is going to be. They've already got the procedures in place. These guys are good. They already have done studies to see how the sound from these offshore wind platforms could impact the marine environment. And so when they're coming to the United States, the Bureau of Ocean Energy Management is requiring them to do that same work. Even though noise isn't, technically a pollutant here in the United States, they're really treating it as one in, environmental impact assessments. If you want to put in a new pier and you're going to do pile driving's loud. You have to be able to determine what your impact is going to be on the environment and take necessary mitigation actions. And I think that's a really good thing. And it's been forward leaning, I think, by the Bureau of Ocean Energy Management to require that, and by the wind companies that are doing the work and we're already prepared to do the work, by the contractors that are doing some of those studies. There's a wonderful company called Jasco based out of Canada. They've got a US office as well. We used to compete with them, but we got tired of losing. So now we work with them as often as possible. But they do just a great job at really understanding the environmental impact of industrial activity on the habitat, on marine mammals, fish, etc. And I think that's really important. So if we take a step back again, you said sort of how do you define noise pollution? There's legal definitions, and that's what we just talked about. But there's just working definitions as well. And I think underwater noise pollution will be sound made by human beings that impacts the environment. And that can be more nuanced and more complicated than it sounds on the surface. With the original example I gave of sound and air, it's pretty easy to determine if that's having a negative impact on human beings. I say easy. It's a study. I mean, it's challenging, and human beings are difficult animals to work with. That's why I became a physicist. But it's possible to ask a person, how are you feeling? It's possible to ask them to come in for regular tests so you can evaluate their health. You can determine if regular loud noises are causing stress hormones like cortisol and aldosterone to increase in their systems. It's possible to stick a camera in their ear, or whatever doctors do. I'm not that kind of doctor. To determine what sort of impact you've had on their hearing. Whales are a little more difficult to get them to come in for regular appointments. I mean, you can't ask them how they're feeling. Moreover, the way they use acoustics is so much more complicated and more nuanced than the way human beings use acoustics. It's hard to know how the sound that we produce impacts them. We use sound to hear, and that's about it. We use them to communicate with each other, maybe find things generally. But whales use sound for everything. Think about this. If I put you in a room with needles on a chalkboard, just constantly going for a month, the sound of needles on a chalkboard, you would lose your mind. Your stress hormones would be elevated. You'd lose sleep. And there would be significant health impacts on you. But there is no physical reason why that should be true. The elevated levels of that sound, the frequencies, there is nothing physically about that sound and how it interacts with your hearing organs, your ears, your eardrums, that should mean that that's really painful for you. The only way that I know that needles on a chalkboard are painful for some people is because we can talk to people. We can't talk to whales about that. We don't know if there's an equivalent of needles on a chalkboard, if the sound of a ship is like needles on a chalkboard for a whale, because the way that they perceive sound is so much more nuanced and so much more complex than human beings. And they're so much more sensitive to sound than human beings that it is difficult. That being said, we can do our best. I've recently been very lucky to participate in a study in collaboration with the World Wildlife Fund, NOAA here in the United States, and PAIM, a working group on the Arctic Council, to predict future noise pollution levels in the Arctic from changes in shipping traffic. And we did a good job, I think. We ran some really incredible acoustic models that we're very, very proud of. We modeled every ship everywhere in the world, all the time, every minute, every day, every month, every year, in order to create statistics on what the sound has looked like, over the last 10 years and what it might look like over the next 10 years. And we showed our results, to our partners at the World Wildlife Fund, and they were like, "Cool, nerds. What does that mean?" They didn't say that. They're very nice. But what we realized is we had all these statistics and decibels and hertz, but it didn't mean anything because it didn't tell us how that sound might actually impact the environment, particularly some of the really, really sensitive and, quite frankly, not well understood species that live in the Arctic. And so what we did is we asked one of our lead marine biologists, Dr. Carrie Seeger, who's brilliant, if she could put together sort of a map by species. And so what she did is she took all the information that we had on the species extent for all of these critical species. So we had maps of where they were. And then she took all the information we had about the audible range of these species as best we could tell, which of course, there might be gaps in our knowledge there, as well as, just because you can hear this frequency doesn't mean it sounds similarly stressful to this other frequency, but it's the best we could do. And then we integrated the sound energy over their audible bands in the area where that animal lives. And we were able to start coming up with sort of risk scores by species, by region, that told us, how much sound energy there would be. But then, of course, there's other differences. A gunshot or an explosion is a really intense sound that lasts for a second, but it can damage irreparably your hearing organs. It can damage your ears and your eardrums. So that's really bad. But similarly, if I played really loud, really bad music at 130 decibels for a month straight and never gave you any reprieve, that would have different physiological impacts on you. You would be stressed. You wouldn't be able to communicate. You wouldn't be able to talk. If you're a whale, you wouldn't be able to navigate, find food, find mates, etc. And so, how you quantify how bad sound is for an organism, has to be classified in different senses. And there's a whole set of guidelines created by NOAA here in the United States, and there's similar guidelines in Europe and all over the world that help us understand what the impact of sound is on marine mammals. One of my favorite studies was by a group called Jamapans in Northern Europe, where they wanted to understand the impact of shipping noise on marine mammals in the North Sea. And one of the statistics they reported on was the percentage of the time that sound was above certain thresholds, that would be either damaging or uncomfortable to marine mammals. And that's really important from a stress perspective. How often can this whale, find mates, etc.? Because, maybe if a ferry crosses through that whale's habitat once every few hours, it's not a big deal because they can still find mates in between. They can still find food in between. They can still communicate in between. But if it's all the time, that really matters a lot as well. So to your original question, how do we define sound pollution? Well, it's man-made sound that affects the environment. But how do we decide what the impact of that pollution is on the environment? I think there's a lot of research that still needs to be done. There's a lot of really good people doing that research, and it becomes more nuanced. And you have to really think about how that sound impacts the environment in order to really, quantify how bad that pollution is so you can take mitigation measures.
Well, thank you very much for that. That was a really sort of detailed look at it, a really detailed overview, and I appreciate it. So, what I heard you say was that it's not just enough to be able to map like the propagation of sound in the sound shed. If we go back to that original discussion about this geographic area is affected by this noise, we also need to have a Venn diagram where we have how does that overlap, how does that affect the animals that are living there, and we could use that to define noise pollution. So I used to work for a company that was building offshore wind parks, and they were experimenting with this idea of using a bubble net, blowing bubbles up from the sea floor to protect the area that they were working in from too much noise, so escaping from the point source. When you think about the future of this, is there a world where we sort of noise proof our shipping lanes, noise proof our other activities? Can we set up barriers in the ocean? Can we use bubble nets? Is there any way to protect the marine environment from the noise that we are creating?
We just submitted a grant, gosh, this week to see about the viability of doing bubble curtains around ships. It's a pretty far out idea. I would say a lot of experts in the field have said that that would be very challenging. First, for the listeners, why that might work. Well, if you're doing pile driving, and let's say you've determined that it's going to be really loud, you've determined that there's a lot of marine mammals in the area, you've done your homework, you've done your due diligence, and you don't want to impact those marine mammals. One of your options is to lay, essentially hosing down on the bottom of the ocean. It's more complicated than this, but basically it's a tube with a bunch of holes poked in it that you pump air through, and it puts these big strings of bubbles, curtains of bubbles around the pile driving thing, and that blocks the sound. And you might think to yourself, well, that seems silly. Why does bubbles block sound? Well, think about it this way: if you've ever been in a swimming pool, could you hear the people talking above the swimming pool? Probably not. Similarly, if you were in a swimming pool and made a bunch of noise, the people outside the pool couldn't really hear you. And that's because the pressure difference and density difference and speed of sound difference between water and air is so great that sound waves sees that boundary between air and water as almost like a perfect reflection surface. So very, very little energy can travel from water to air and vice versa. So if you start putting all these little bubbles in the ocean, you create like a wall where the sound sort of reflects off that wall and it can't propagate through it. So in theory, bubble curtains can be a really effective mitigation strategy. And for things like pile driving, where you have one giant structure that you can ring with hose, that's definitely viable. It's it can be done well and it can be done poorly. So For all you bubble curtain people out there, please do a good job. But it's an effective thing. By the way, I feel like I can't talk about bubbles without talking about the Bubble King. There's a researcher at the Knock in Southampton named Tim Layton. We call him the Bubble King. It might be just behind his back, but he wrote like an 800-page book called The Acoustic Bubble about the acoustics of bubbles. They are indescribably important. The bubble acoustics can cause sound to be trapped in the surface. It affects underwater communications. It affects everything. So bubble acoustics is an entire discipline of study that is really, really important for reasons like this. To your question, can we just soundproof entire shipping lanes? Most people would just flat out say no because it's going to be too expensive. Shipping lanes are massive, but maybe just in places where it really matters, right? Maybe just in places and maybe just in places where you have a shipping lane going through a critical habitat. Look at the Santa Barbara Channel in the United States. LA Long Beach is the highest volume port in the United States, and a lot of vessels, the most efficient route is to go through the Santa Barbara Channel. It's habitat for a ton of highly endangered marine mammals and other species that are sensitive to sound. What about in places that are just really, really sensitive? Could we do things like shield shipping lanes with bubbles? Maybe. Yeah, maybe. Entire ports? Maybe. Yeah. I don't think we've done enough work to rule that out. Or similarly, if you're in a ship that operates often in areas where species might be really sensitive to sound, could you sort of inject a bubble curtain around the whole of your ship? It would be very challenging. A lot of significant engineering challenges to be able to do something like that. Icebreakers actually inject bubbles along the whole of their ship to reduce the friction with the ice. So there are systems, albeit a lot less complex, that do things that are similar. But like I said, a lot of significant engineering challenges to do it, but I don't think it's impossible. And also there might be other ways to reduce the sound from ships. If you've ever been in the engine room on a ship, I wear hearing aids because after my time in the military on ships and all the low frequency vibrations for so long, apparently that kind of degrades your hearing over time. Engine rooms are loud places, and there haven't really been a lot of standards to try to make them quieter. There are really good engineers out there who specialize in making things quiet. You would never accept a car that was so loud that you could never hear anybody while you were inside of it. That's because really smart engineers tried very hard to make those things quieter. So I think there's probably a lot of gains to be had just purely in engineering of ships. I forget the name of the company, but some folks have designed these sort of, they're not springs, but basically shock absorbers that you mount things like your generators and engines on. That sort of decouples the vibrations from the machinery with the whole of your ship, which prevents some of the acoustic emissions. And there's a lot more that can be done. Well, think about it this way: the Navy's been trying to make submarines quieter and quieter for going on 80 years now. So taking some of that engineering and applying it to commercial shipping, it'd be expensive. But yeah, I think there's a lot more work to be done there. And I think as more and more people start to think of sound as a pollutant, there are going to be requirements that come out that make us take some of those engineering steps.
Wow, we have come a long way in this conversation, and I'm really enjoying it. So this has been absolutely great for me. You're working on a ton of different things. You're exposed to a ton of different ideas. Is there what's the thing out there that's got you most excited for this year, and maybe for the next 5 years?
Oh man, that's a tough one. You might be able to tell I get very, very excited about my work. I love oceanography and I love ocean acoustics for all the reasons we talked about. There are so many unsolved problems that are really, really important.
Let me just stop you there. You talk about unsolved problems that are really important, and it sounds like you're excited by this. So you're not overwhelmed by the challenges. You're excited by these unsolved problems.
Yeah, yeah, of course I'm excited. I don't know about you, but if I do something that I think is impactful, it makes me happy. It makes me think like I made a difference. And if I can make tiny little advances in our understanding of underwater sound and of the ocean, I think that there are huge benefits to society and to the world. And yeah, that can't be anything but exciting that there are so many problems that I could contribute in a small way to solving that can make the world a better place, that can help us understand how to protect whales better, that can help national defense, that can help us address climate change. So yeah, that the amount of unsolved problems that are solvable in our time in the ocean and how impactful those solutions would be to humanity is what gets me up in the morning. It's really, really exciting. So to your question, there's two projects that have me most excited right now. One of them because it's just so darn cool, and the other one because it's so darn hard. And so the one that's cool is the project I told you about already with the World Wildlife Fund and the Arctic Council and NOAA. First of all, our government program manager is wonderful. She has us solving hard problems. She's pushing us hard to really do the best job possible to understand how shipping noise in the Arctic is likely to affect Arctic ecosystems in the future. And we have just gone all out. We've taken the most sophisticated acoustic propagation models we've ever made and parallelized them and optimized them for all sorts of computing architectures to be able to simulate every ship everywhere all the time. We've brought in marine biologists, ecologists, physicists, atmospheric scientists. We'll get to work with the World Wildlife Fund, some really incredible and passionate people in those organizations to try to come up with a prediction of what the soundscape is going to look like in the Arctic over the next 10 years and what the impact is going to be on ecosystems. And I think the work we're doing is good. It's really good. We've gotten to work with world experts and everything from economics that'll drive, how shipping will change to some of the best ecologists and marine biologists there are, Department of Transportation people who just get shipping traffic. And the work is good and it will be delivered by World Wildlife Fund, by these Arctic Council people to decision makers who will get to look at these maps of, oh, there's a shipping lane here and there's a critical habitat for this whale there. Maybe if we just moved this shipping lane, or maybe if we made, this regulation or that regulation, it would have this huge impact on the future of conservation in that really critical environment. So I think the combination of how good the work is, the fun people we get to work with, the potential impact the study has, that one is just really, really exciting to me. And then the second one that has me really excited is one we've alluded to, but it's a basic research program funded by the Office of Naval Research here in the United States. It's about the information content of ocean noise. It was inspired by work done by my PhD advisor, Dr. Bill Cooperman at Scripps a few years ago, where we're trying very, very hard to understand everything you can learn about the ocean from sound that's already in the ocean, be it from ships, be it from whales, regardless of the source. How can we better understand what we can learn about the ocean from underwater sound? And I've had a chance to collaborate with brilliant scientists at Scripps, at Georgia Tech, and Woods Hole, and Portland State, University of Washington. In my own company at Applied Ocean Sciences, and it's so darn hard. The math, the work you need to do to try to synchronize all your clocks and position all your ships and your sensors and parameterize the ocean in really clever ways to sort of reduce that mathematical search space. It's so darn hard and therefore very rewarding when we make progress. So yeah, those are the two most exciting things I'm working on: the ocean conservation, noise pollution stuff in the Arctic because of the impact, and the information content of ocean noise stuff for the Navy because it's so hard and so interesting, and I also do think critically important.
Chris, I really want to thank you for your time. I have thoroughly enjoyed talking with you. You're brilliant, you're enthusiastic, and you're human. This has been a really inspirational conversation for me. So I really appreciate it.
Well, don't tell my physicist friends that I'm human. Then that'll lose all of my street credibility.
I'll keep it to myself. But let's say somebody else is listening to this and they think, well, who is this guy? How do I get in touch with him? How can I reach out to him? Where would they go to do that?
Well, yeah. I mean, if anybody after this still wants to hear more, yeah. So the Applied Ocean Sciences website has contact info. I mean, it's Applied Ocean Sciences. Make sure you get that sciences at the end .com, and then also my email is chris.verlinden at appliedoceansciences.com. I'm always happy to talk acoustics with anyone and everyone. So again, that's chris.verlinden, Verlinden at appliedoceansciences.com. And feel free to cold call me or email me. I love talking about this stuff. Thank you for having me. I don't know if you had fun, but it's not often I get to talk about information content of ocean noise and how I lose sleep over beluga whales. And it's clearly something I'm excited and passionate about, and really always happy to share that with anybody who will listen. So yeah, please tell your viewers, anybody who wants to get a hold of me, don't be afraid to reach out.
Thanks again, Chris. This has been fantastic.
Thank you.
So once again, a big thank you to our sponsor, Regrid. If you are looking for parcel data for the US, regrid.com would be a great place to start. I'll put a link to them in the show notes to make it a little bit easier for you to find. So I really hope you enjoyed that episode with Chris Verlinden, CTO and Vice President of a company called Applied Ocean Sciences. I think I mentioned this at the start of this episode, but we covered a lot of ground here today. And I think if you want to recap any of these key points, the best place to do that will be on our website, mapscaping.com. There'll be some in-depth show notes there. And if you're interested in following up on any of these things or looking for links, that would be a really great place to start. So this episode ties in really well with the previous episode that I've published called Mapping the Ocean Floor. That was published in January 21, and I think if you want to know more about that, more about the Seabed 2030 project, that would be a great place to start. Again, I'll put a link to that in the show notes to make it easier for you to find. On a slightly different note, I would really like your help. So this year I'm going to be putting a lot of effort into building more sustainability around this podcast. What I've discovered in the last 3 years is that I simply can't do this by myself. So if you're interested in helping me, if you're interested in supporting this podcast, there'll be a link in the show notes today to a Patreon page, and this is an opportunity to provide a small monthly financial contribution. This is one of those things where even a little bit would mean a lot. I would really appreciate your help with this. Okay, that's it for me. That's it for another episode of the Mapscaping podcast. I'll be back again next week. I really hope that you'll take the time to join me then. In the meantime, you'll find a bunch of show notes, links, all sorts of resources at mapscaping.com. If you don't want to keep going back to the website, just sign up for the email list and I'll send them out to you each week. Okay, that's it for me. We'll talk again soon. Bye.